Hello everyone, I am Vidya Patil, Assistant Professor in Department of Mechanical Engineering in Sharad Institute of Technology, College of Engineering, Yadra. Today in this session we are going to learn the introductory part of thermal engineering, and in this session we are going to cover the Zeroth Law of Thermodynamics, first law of thermodynamics and its application, limitations of first law of thermodynamics and second law of thermodynamics and its application. First, we start from Zeroth Law of Thermodynamics. The Zeroth Law of Thermodynamics is a fundamental principle that is essential for understanding heat and temperature. It is used in wide variety of applications, from cooking, refrigeration to the design of engine and power plants. So, the Zeroth Law of Thermodynamics states that if two systems are each in thermal equilibrium with third system, then they are in thermal equilibrium with each other. In simpler term, it means that if two objects are at the same temperature as a third object, then they are at the same temperature as each other. You can see in this figure. But here the new term, that is thermal equilibrium. So first we understand the term thermal equilibrium. So we know that temperature is a property that distinguishes the thermodynamics from other sciences. This property can distinguish between hot and cold. When two or more bodies at different temperatures are brought into contact, then after some time they attain a common temperature and they are said to exist in thermal equilibrium. So systems are said to be in thermal equilibrium if there is no heat transfer, even if they are in a position to transfer heat based on other factors. For example, if we put a food in a refrigerator overnight, then the food is said in thermal equilibrium with the air of the refrigerator. Heat no longer flows from food to the air or from the air to the food, and this state is known as the thermal equilibrium state. So the Zeroth law is a fundamental principle of thermodynamics, and it is used to define the concept of temperature. So temperature is a measure of hotness or coldness of an object, and it is determined by the amount of thermal energy that the object contains. So the Zeroth law states that two objects are at the same temperature if they do not exchange heat when they are brought into contact. Zeroth law is also used to explain why heat flows from hot object to cold object. When two objects are at different temperatures, they will not be thermal equilibrium. If the objects are brought into contact, heat will flow from hotter object to colder object until the two objects are at the same temperature. This is because heat always flows from hot region to cold region. So the Zeroth law has a number of important implications. If we take the example, many examples are there. It allows us to use thermometers. Thermometer is one example to measure the temperature. Thermometer is a device that contains the substance that expands or contracts when its temperature changes. When thermometer is brought into contact with the object, the substance in thermometer will expand or contract until it is in thermal equilibrium with the object. So the temperature of the object can be read from the scale on the thermometer. So the Zeroth law states that here in this figure we can see here there are three systems, system A, B and C. System A and B both are thermal equilibrium with each other. System A and C again thermal equilibrium with each other. That's why again system B and C also thermal equilibrium with each other on basis of the Zeroth law of thermodynamics. Here some examples of the Zeroth law in action. That is, if you put a cup of hot coffee in a bowl of cold water, the coffee will eventually cool down and water will heat up until they are both at the same temperature. Again, second example, if you put two ice cubes in a glass of warm water, the ice cube will melt and the water will cool down until they are both at the same temperature. And third example, if you touch a hot stove, your hand will get burned because heat will flow from stove to your hand. Now we see the first law of thermodynamics. The first law of thermodynamics is a statement of energy conservation, which states that energy cannot be created or destroyed, only converted from one form to another. So this law is also known as the law of energy conservation or principle of energy conservation. It is fundamental law of physics that applies to all physical systems, including thermodynamic systems. The first law of thermodynamics can be used to predict the thermodynamic system's behavior and determine the changes in the energy that occur during various processes. It is important law used to understand the system's behavior and design new energy technologies and devices. Here, in first law of thermodynamics, the equation is there: delta U is equal to Q minus W. Here we know that Q is the heat supplied or heat and W is the work done. So now we see the different applications of first law of thermodynamics. Here I list out the applications, that is in automobile engine, human metabolism, refrigeration, electric power plant, solar panels, battery charging, hydraulic system, wind turbines, food cooking, and nuclear reactors. I explain one by one. First we see the automobile engine. How first law of thermodynamics is used in automobile engine. So when you drive a car, the process begins at the fuel pump. When you fill the gas tank with the gasoline is a chemical fuel that contains the amount of potential energy stored in the form of chemical bonds between its atoms. So that potential energy is often referred to as a chemical energy. So in this process, the first law of thermodynamics is evident. The energy within the system is conserved as a chemical energy in gasoline and is transformed into the combination of kinetic energy because of the movement and thermal energy which is released as a heat. So this example illustrates the fundamental principle that energy neither created nor destroyed. It only changes form or is transferred in accordance with the first law of thermodynamics. As we start the car engine, the chemical energy stored in gasoline is released through a controlled combustion process, and after the combustion, the movement of the piston is converted into the rotational movement of the engine crankshaft, and again rotational crankshaft is connected to the car wheels, and through the series of mechanical components it transfers the mechanical energy to the wheels. This mechanical energy again ultimately transferred into kinetic energy, which is energy of the motion, and that propels the car forward and allow it to move. While the conversion of chemical energy into kinetic energy is the primary goal, not all the energy is effectively converted. Some of the energy is lost heat due to the inherent efficiencies of the engine. So this is the one example of the first law of thermodynamics. Second example is human metabolism. This is one example where the first law of thermodynamics is used. When you consume the food, your body extracts the chemical energy stored in the micronutrients such as carbohydrates, fats, proteins, and this energy again through metabolic reactions within cell to power a range of psychological function. So some of this energy is converted into kinetic energy, enabling you to move, exercise, and perform daily activities. Additionally, a significant portion of this energy is transferred into thermal energy to maintain your body temperature at a constant and optimal level. Again, this process is known as the thermoregulation, is essential for your survival. It is as it ensures your body remains with the narrow temperature range. So again, this way your human metabolism is the remarkable example of the first law of thermodynamics in action. Again, in next example is the refrigeration. Refrigeration is a practical application of first law of thermodynamics, where where the showcasing how energy can be effectively transferred from one location to another to achieve a specific goal. In the refrigerator, its primary function is to maintain the cold environment while its insulated compartments, and it utilizing the refrigeration cycles, which involves the coolant refrigerants that circulates through a system of coils and components. So again, this is one example of thermodynamics. Again, electric power plant, solar panels, battery charging, these are the different examples where the first law of the thermodynamics is used. Next, now we see the limitations of the first law of thermodynamics. Here I list out the three limitations. That is, the first law of thermodynamics fails to give the feasibility of the process or a change of state that the system undergoes, and it fails to explain the direction of heat flow also it doesn't say the process is spontaneous or non-spontaneous process. So we see one by one. First law does not say anything about whether the process is possible or not. Here you can see in image, you can see that in engines the chemical energy of the fuel is converted into useful mechanical work, but we cannot convert this mechanical energy back into fuel. So, or in other words, if we say engine cannot produce fuel back again, so we all know that this is practically impossible. So but the first law of thermodynamics does not say anything about it. Thus it is the one of the limitation of first law of thermodynamics. Again we see the next figure, that is first law of thermodynamics does not say anything about the process will occur on its own or not. That means if we take one question like what will happen if you put the ice on table, it will melt down after some time or its own. Now what about the reverse process, water to ice, what will be occur in own? No. So we all know that the conversion of water into ice does not occur on its own, but first law of thermodynamics does not say anything about this. That means the first law of thermodynamics does not say whether this thermodynamic process occurs on its own or not, and first law of thermodynamics does not tell us whether the process is spontaneous or non-spontaneous. So again, in third, the first law does not provide any sufficient condition for a certain process to take place. If we take the example that already we know that heat always flow from higher temperature body to lower temperature body. So but in reverse process it does not possible. So now if we want to make this reverse process possible, then will it occur in own? No. Can we transfer heat from lower temperature body to higher temperature body without doing anything? Is there any condition for transferring heat from lower to higher temperature body? So here we know that there is no not first law of thermodynamics not provide anything sufficient condition for the certain processes. Okay, so these are the limitations of first law of thermodynamics. Now we see the second law of thermodynamics. So second law of thermodynamics statements there are two statements, Kelvin-Planck statement and Glossier statement. So the Kelvin-Planck statement said that it is impossible to construct a device which operates on a cycle and produces no other effect than the transfer of heat from single body to produce the work. This means that it is impossible to construct an engine whose sole purpose is to convert the heat from high temperature source or reservoir into equal amount of work. As we know that heat is the Q and work W are the two forms of energy. Both follow the SI units joules and both are interconvertible. This means work can be converted into heat and vice versa. Here work can be fully converted into heat, but heat cannot be fully converted into work. Hence work is called as the high grade energy and heat is called as a low grade energy. The Kelvin-Planck statement is the two different statements, Kelvin by Lord Kelvin and Planck. They are known as the Kelvin-Planck statements. So Kelvin statement states that it is impossible to derive mechanical effect from any matter by cooling it by below the highest cooling temperature of the surrounding objects, and Planck states that the total sum of entropies for the reversible system remain constant. So clubbing these both statements, Kelvin-Planck statements, was derived. So this statement is also known as heat engine statement from the second law of thermodynamics, which say that is impossible to design a device that work on a cycle and produces no other effect other than heat transfer from single body for the production of the work. So next is the Glossier statement. So Glossier statement said that it is impossible to construct a device operating in a cycle that can transport heat from cooler body to a warmer one without consuming any work. So also energy will not flow spontaneously from low temperature object to higher temperature object. So it is important to note that we are referring to the net transfer of energy. So energy transfer can take place from cold object to hot object by the transfer of energetic particles or electromagnetic radiations. So however, the net transfer will occur from hot object to cold object in any spontaneous process, and some form of work is needed to transfer the net energy to hot object. So unless the compressor is driven by the external source and the refrigerant won't able to be operate. So the heat pump and refrigerator work on these Glossier statements. So both Glossier and Kelvin statements are equivalent, that is, a device violating Glossier statements will also violate the Kelvin statements and vice versa. So these are the applications, that is refrigeration, which transforming heat from cold reservoir to hot reservoir, that is required work input. Second, heat engines, where converting heat into useful work, that is the limited by the Carnot efficiency. And third is the material science, that is predicting material stability and phase transitions. These are the applications of the second law of thermodynamics. Okay, in this session we cover the first law of thermodynamics, second law of thermodynamics and its applications. Thank you.